Hello, thank you for attending my presentation today. My name is Kevin Hepner and I work for SysCAD. My presentation is on dynamic modeling of ion exchange processes for uranium. Here is an overview of what I will be discussing today. First of all, we will review what a process model is. We will look at the ion exchange mathematical model that was employed in this study in detail. We will then use this mathematical model to perform a dynamic simulation. Then the dynamic simulation will be used for a parametric study. And finally, results will be summarized. First of all, what is a process model? We hear the term digital twin often, but what does it mean? Well, a digital twin is just a process model that represents your system using a mathematical representation. Well, a good model will always give good absolute predictions. The real strength is in comparison of scenarios. Quite often, the difference between scenarios is the most accurate and often the most important output from a model. Model development can follow the stages of a project, from feasibility through to plant operation, and then looking at plant maintenance, expansion, and back to feasibility again. This process is circular as your process and operation project evolves and changes. Now that we've talked a little bit about what a model is, let's look at the particular problem we are looking at today. What you see in front of you is a block diagram of the plant model in SysCAD. This is a model of a 3-train, 1-elution system plant for uranium. If you follow the yellow lines, you will see the movement of uranium through the whole plant. It is loaded in the loading trains onto a column. Then loaded resin and barren resin are exchanged between the loading train and the elution column. Overall, the uranium impregnant solution is purified and concentrated to form uranium-rich eluate. Let's look now at the individual column model. The plant model I just showed you has 10 individual columns, 9 used in the loading trains and 1 used in the elution system. Each column is modeled using an FEM approach with time, so finite element model. Using this approach, a dynamic profile along the resin length is predicted via dynamic mass balance with chemical reactions applied at each slice. This is the chemistry model that was employed in the model. The loading model uses a Langmuir isotherm, which was published by Dunn. The elution is done by sodium nitrate and conditioning by sulfuric acid. We have assumed 100% conversion in elution and conditioning because this is conservative for reagent consumption. Now let's look at the logic implementation for each column. The column is modeled as a state machine with multiple states that it can be in. For instance, operating, where the column is receiving production fluid, draining, where the interstitial fluid is gravity drained from the column, washing, where process water is used to wash residual interstitial liquid from the column, conditioning, where sulfuric acid is used to convert resin from nitrate to sulfate form. This is only done in elution. Emptying or filling states, where the resin is being transferred out or in from the column, or idling. The logic for this is programmed in the SysCAD PGM language, and it is done in such a way to optimize code reusability and maintainability. This gives a logic diagram for the loading column. So basically the logic of the state machine. The overall logic forms a cycle as the column goes between each possible state. Different operating conditions will affect individual state cycle times, which will affect the overall capacity of the column. Here is the logic diagram for elution. Comparing it to the previous slide for loading, the main difference is a conditioning step. Similarities between these logic diagrams is leveraged to use common code for the logic. This is the base case conditions which are applied to the SysCAD process model for the ion exchange plant. Loading and elution conditions are shown in these tables. These are typical values, but they're not taken from any particular plant. These inputs will affect the overall cycle time, and hence they will affect the plant capacity. Here we have an animation of lead, lag, polish, column configuration for baseline conditions. First, we start by loading of the column. So pregnant solution is being added. After this is completed, the column drains. Once the column is finished draining, wash water is added to the lead column to push residual pregnant solution to the lag column. After this, the column waits for the elution column to be available. Once this elution column is available, in other words, it's not servicing another train, the resin is transferred from the lead column to the elution column. The elution process proceeds. However, once completed, the barren resin is returned. The former lead column becomes the polish column, the former lag, the lead, and the former polish, the lag. So therefore, each column will go from polish to lag to lead, and then be eluted in the loading cycle. So we will see production fluid 3 times in different strengths. The cycle continues for all 3 loading trains concurrently, with sharing of 1 elution column in this process. For elution, elution starts with the addition of sodium nitric acid solution. This desorbs the uranium from the resin and brings it into solution. After elution is completed, the column drains. Once drained, the wash water is used to wash out residual eluate, and this minimizes uranium loss during conditioning. Sulfuric acid is then used for conditioning to replace nitrate with sulfate on the resin. The conditioned resin is then transferred back to the loading column from where it came, and the cycle continues. Now that we've looked a little bit at how it operates at the bulk scale, let's dig a little deeper into what's happening inside each of the columns. This figure shows a traveling wave of uranium through the resin bed of the lead loading column. As colors of the profiles go from lighter to darker, this indicates the passage of time, with each line separated by 1 hour. In this particular model, from the baseline conditions, breakthrough occurs when the right side of the profile goes above 50 milligrams per liter. So you can see that the last profile, the darkest profile, achieved breakthrough. This figure shows in detail what's happening inside an elution column. Here we see uranium transport through the elution column as predicted by the model. A plug of uranium forms in the column, which moves through the column. Again, lighter to darker indicates passage of time, with each line separated by 1 hour. So you can see the formation of plugs. Initially, when you would add solution, you could see that there would be no uranium in the discharge. Only once the profile reaches the right-hand side of the profile would you actually start to measure uranium in the discharge. Some observations from this. We can see that elution occurs much quicker than loading, and this is due to higher uranium concentration in the eluate. In both cases, a traveling wave of concentration develops in the column, and you can see that the loading and elution are kind of inverses of each other. Breakthrough for either of them occurs when that wave of uranium reaches the end of the column. One thing about this is that for this calculation, open literature data for an isotherm was used in this calculation. These isotherms can be obtained from relatively simple bench scale test work. Thus, this type of a model is a good way to leverage your bench scale test work and to encapsulate it within a model. If you were going to use a model like this example project in your operations or design, it would require validation against plant or pilot plant data. In this project that we have here, it is a demonstration project, and we do not have plant or pilot plant data to compare against. Once you have a working model, it can be used for simulating different operating conditions. You can look at baseline conditions for simulating typical operating conditions for model validation, etc. However, sensitivity analysis can also be used to determine what variables have the greatest impact on key performance indicators. These selected variables can then be changed from baseline values and their effects trended. Here we have the results of this sensitivity analysis. These are time averaged values, simply because there actually is no steady state in this type of a model. The base case on the far left-hand side is for our normal operating conditions as we defined before. Now, each case in front of you looks at a plant change that could reduce plant performance. So for instance, if we compare the base case to the reduction of pregnant solution flow to train 1, we can see that train 1 utilization increases. And this is because there's a longer cycle time for loading, because that case versus the base case has a lower flow of pregnant solution to train 1. Hence, it takes longer to load the resin. In addition, the elution system utilization decreases with lower production rate, because the elution system directly trends with production rate. If we look at the next one, we look at reducing pregnant solution head grade. Here we have a uniform reduction of pregnant solution head grade fed to all of the trains. Again, comparing to base case, we see an increase in loading utilization for all of the trains, and this is due to a longer cycle time for loading. The reduced production rate that results from this also results in a lower elution utilization, because these are directly linearly coupled. Following this, we can look at what happens when we reduce eluent flow. Lower loading utilization happens because we are waiting longer for elution. Because elution takes longer because we have slowed down the flow of eluent without changing its concentration. The elution utilization increases because the elution cycle time takes longer. And there is a decrease in production rate simply because of the decrease in utilization of the loading trains. Essentially, they're waiting for elution. They're spending more time waiting, less time having their resin eluted, each of the trains. Finally, we look at increasing wash time. When we increase wash time due to some reason to do that, we see that wash time is increased for loading and elution. Because washing is considered part of utilization, it doesn't markedly affect the utilization. It does only slightly. And there is a decrease in production rate simply because of the cycle time of all the processes take a little bit longer. In conclusion, we have shown a dynamic model of ion exchange, and we've demonstrated that it's useful for understanding process dynamics in an ion exchange process. It can also be used to understand impacts of operational issues and changes. It's important for assessing process bottlenecks by evaluating equipment utilization and understanding what equipment is being maxed out and what equipment has capacity. Process visualization is important for training of operational staff, and required data for this model can be obtained from bench scale test work. I would like to acknowledge the references that I used in this work, and I thank you for watching my presentation today. Please feel free to contact me should you have any questions.